All right, it is a great pleasure to be speaking on behalf of Stanford University today. As introduced, my name is Will Chu. Today, I want to share some experience with you on the intersection of Silicon Valley and the energy transition. And I'm going to use a case study on battery innovation to tell you how things are occurring today in the Bay Area regarding developing new innovations for the energy transition. So let me begin with some take-home messages. First, and most important, we need to have a diffuse interface between industry, startups, national laboratories, and academia. This really underpins Silicon Valley's success in multiple revolutions over the past 30 years, starting with microelectronics in the 1980s, information technology in the 1990s and 2000, healthcare over the past 20 years, and now the energy transition. All of them shared this very diffuse interface between these four stakeholders. The second message I want to offer here is in developing technology for the energy transition, we are often coordinating many different R&D efforts at the same time. And systems level thinking is the key toward combining and coordinating these efforts. And then finally, I think as many of you recognize, the pace of research and development we have today is not at the sufficient pace to reach the climate goals. We need to be tackling these energy transitions much faster, especially in terms of the technology development time. So let me get into it. So I want to present a little bit of the Stanford lesson, what we have learned in working with industry over the past 20 years in the energy area. This diffuse interface is learning from both academia and industry at the same time. On the left, we have what we do very well at universities, which is fundamental understanding, small-scale proof of concepts. We also are very good at operating big science facilities, and also we're able to embrace new directions. For example, machine learning really first took a stronghold in Silicon Valley 15 years ago. On the other hand, industry has many interesting specialties that academia does not have. For example, it has strength in prototyping and scale up. Industry is very good at optimizing very large problems, and it has the system integration thinking and, of course, the business model. And what we've been practicing here at Stanford is to try to take the best of both worlds. To do so, we have to do it at a pre-competitive basis. So we are openly working with as many industry partners as possible and bring the understanding into our students, postdoc staff, and faculty. There is only one metric of success when you combine the two together, and that is to de-risk technology for commercialization. So this is the model we have been running over the past 20 years in the energy area, and this is the model we're using in order to deliver the innovations for the energy transition. So let me now briefly showcase some of these partnerships. Just in the area of batteries, this is a very exciting topic, especially to many of the industry leaders in Korea. We are also working with virtually the entire value chain here at Stanford, collaborating with people all the way from mining to refinery, to materials, to battery cell, to battery system, to recycling. And we're able to co-innovate with these industry partners, meaning that they not only bring financial support for these efforts, but they also bring the industry knowledge, as I presented on the previous slide. What is even more exciting, being located in Silicon Valley, in the battery area alone, Stanford has spun out 9 companies in the past 10 years. Several of these companies may be recognized by you as emerging leaders in this area. And this is really the DNA of Silicon Valley, of Stanford, is successful technology is transferred outside to the university into Silicon Valley. And the origin of this is by allowing our students and faculty to work very closely with industry in order to really fully understand what the real problems are. So with that general introduction, I now want to talk a little bit about batteries themselves and why this is a really good model system for developing new approaches, for developing innovations for the energy transition. So first of all, batteries are extremely complicated. In fact, if you think about all of the process in the battery, they span all the way from 1 nanometer all the way to many meters, to the size of a car or a BESS system. And if you think about the time, it goes from picosecond, so 10 to the minus 12 seconds, to many years. And you span many different concepts from quantum mechanical understanding all the way to device operations and control systems. And the important lesson here is that not a single entity, not a single company can really master this entire scale. And at a university, we are particularly well positioned because we have domain experts in all of these areas. What we lack is we lack focus. We don't have the focus as companies do to ship a product, but what we gain is we have an interest in understanding and connecting everything together at the systems level. So as I mentioned earlier, we are very good at using our toolboxes. We are understanding and developing synthesis and manufacturing. We are developing analytics, modeling. And at the end of this, we're able to piece every piece together to develop this holistic understanding. We are not as relevant as industry can deliver, but we deliver the most fundamental insight, and also we link everything together as best as we can. So next, let me give 3 examples of systems level thinking that we have been working on for the past 5 years at Stanford. The first one I want to mention here is fast charging. So if you consider the electric vehicle revolution, really one particular bottleneck is the so-called range anxiety. And one way to mitigate the range anxiety, in addition to making more energy-dense battery system, is to develop faster charging solutions so you can recharge the car faster. The typical goal is 5 to 10 minutes to charge a car to 80%. So that will be very similar to a gas refueling. But this brings about several major systems level problems. First, to calibrate the energy scale, to charge a 100 kilowatt hour battery in 5 minutes will require 1 megawatt, which is roughly 1% of a Boeing 737 airplane taking off. So this is a huge amount of power. And if you just consider the state of California, if we have 5 million EVs in 2030, and the projection will go beyond this based on current numbers, if all of the fast charging is happening at the same time, it will require double the capacity of our energy grid in California. So this directly highlights the scale of the problem. So why do we require system level thinking? Well, if you think about fast charging, it goes all the way from the grid to the charging station. So this concerns high power electronics, high efficiency electronics. You have to think about the vehicle, how to deliver the charge. You have to think about the design of the battery pack in terms of how to integrate thermal management. You have to think about the battery cell in terms of how you design the battery architecture. And then finally, at the materials level, we also need materials that can handle this type of charging speed. So this is a very good example why this problem cannot be viewed only one box at a time, but you have to put all of these boxes together. And inevitably, you have to develop the technology together with great deal of intersection between the technology. And one argument I would like to make here is that there's still a lot of opportunities to coordinate these R&D activities because they're usually siloed in different companies within industry. So this is one area that Silicon Valley is trying to address by a closer collaboration between universities and startups. The second systems level problem I would like to share with you is the battery circular economy. This has received a lot of attention because of real needs for battery recycling, but also the economic opportunity. The estimate 2 years ago, and this number is now much greater, is that we will have about a $10 billion market for so-called second life batteries. But the problem is much bigger than just a battery recycling problem. The way we have presented this problem as a systems level problem is that it's really about decision making. When you use your battery and it has reached the end of its life, you have to think about what to do with the battery. But recycling is not the only option. For example, you can reuse them in the same application, maybe in a different kind of vehicle. You can regenerate them to remanufacture the battery. And you can also think about putting into a second use, for example, for grid level energy storage, for ESS application, or you can recycle them. So today, we do not have the ability to really make this decision on a quantitative basis. And here, the decision is an economic one. You have to think about what is the value of the battery in its future applications, and also what is the cost of the battery you have to recycle. And this is, again, a very big systems level problem. And we are integrating our expertise in data science and thinking about how to predict battery performance in different usage scenarios. We are doing systems engineering at the battery pack level so that we can easily rejuvenate and also take the battery out and recycle them. And we're also developing new materials, which has a lower cost for recycling. So again, I want to showcase this as the second example of why something as simple as battery recycling can actually be a very complex problem. And one thing I want to point out here is Korea is very well positioned in terms of its battery industry and also the large corporations that has the ability to integrate the system. And I think this is a very, very large business and technical opportunity for Korea to tackle. The final systems level problem I would like to share with you here is the battery value chain. So the battery value chain is extremely long, extending all the way from raw material mining to battery material manufacturing, to battery manufacturing, to device integration by OEMs, to recycling. So why is this a systems level problem? Well, it turns out anytime you change any part of this value chain, you have to evaluate, you have to optimize, and you have to make decisions. And every time that decision is made, it's very capital intensive, it's very time intensive, and also it's very people intensive. And they're extremely coupled in the sense that one decision will affect another. So this is another major problem in which it's a very challenging problem for one single entity to tackle. And again, coming to my take-home message, this is where universities can become a very powerful convening place to bring all the knowledge together and try to understand how to deploy new technology for the energy transition in a very efficient manner. So let me also now just share with you a couple of things we do well at Stanford to share some of our latest findings. So I want to give you 3 highlights. One is show you the most fundamental understanding and how much of this learning can translate into practical design rules for better batteries. On the left here, I'm showing the first atomic image of lithium metal, which was taken here at Stanford by my colleague, Professor Chueh. In the middle, we have an image of a single battery particle that is being charged and discharged. And on the right, we have a CT scan of a battery particle that is being charged and discharged. So these are very, very basic science, but they're paving the way to understanding how batteries are synthesized, how they are manufactured, and how they age and degrade. And this level of fundamental understanding is really what has been driving Stanford to develop the fundamental science. The second level, beyond the fundamental understanding, we have also been developing many new materials and new chemistry. Fundamentally, batteries are governed by the type of materials that go in it, and step changes in the performance, such as energy density and safety, ultimately will have to come from material advances. And here I'm just showing you some very nice pictures. For example, the development of silicon batteries originated from Stanford. The development of safe polymers for cell healing batteries also came from Stanford, so on and so forth. And these constitute the type of advances that we are able to make at the materials level in order to deliver new battery technology. The final set of example I would like to make here has to do with AI. So AI has received a lot of attention in the past decade. But sometimes it's a little bit difficult to see what is noise and what is really significant. And here I want to show you two examples from Stanford that we're very proud of. On the left here was the work of my colleague, Evan Reed, who used machine learning to accelerate the discovery of new materials. In this particular case, he was looking at the discovery of new solid electrolytes for solid-state batteries. And he pioneered methodologies which takes a process that would ordinarily take about a month to predict to only 1 second. And this advancement in terms of computational material discovery is truly game-changing. And we have seen also very similar successes elsewhere in material science, whereby AI and computational material discovery can be combined to really identify useful materials that can make a difference. The second example is one on lifetime prediction. So one of the big challenges with battery technology is that the lifetime is very long. So the iteration design cycles are typically at least 1 to 2 years for a new battery cell and 3 to 5 years for new battery chemistry. And this is really, as I mentioned at the beginning of my talk, a key limiting factor in terms of the speed at which we can deploy new technology for the energy transition. So in this particular work, which I'll talk to you in greater detail, we're able to really cut down that time from many years down to weeks and sometimes even to days in order to accelerate the materials innovation cycle. And this is something that I think is having a really large impact in battery field and beyond in a way that is not foreseen previously as a true disruptor in terms of technology development. So let me just highlight, this is the work that came out of my lab here at Stanford, and it was covered by the Wall Street Journal a few years ago, where we have demonstrated the ability to really speed up by about 30 times the development cycle for new battery technology. And this is really, as I mentioned before, the key to deployment, because we really have to think about the speed at which we do things. Let me show you one more slide on the technical detail. Essentially, what we have done is to use an artificial robot to teach us how to optimize new battery chemistries. And the speed enhancement is truly phenomenal. So this is a setup that we have created at Stanford about 4 years ago, and now is being widely used by others as well, and has led to one spin-off company. Let me just share with you how it works. It basically allows the computer to make very informed decisions in order to reduce the number of iterations needed to optimize a new material. Currently, it takes about anywhere from 10 to 50,000 iterations to take a material from laboratory discovery to commercialization. And in this particular example, we have been able to take a process that would ordinarily take about 2 years down to just half a month. So this 30x enhancement is resulting in a completely new paradigm in terms of how quickly materials can be designed. And the way this is done is by combining very good and base understanding of the science, AI algorithms, and also rapid experimentation. And by spinoff here, Mitrachem has been pioneering this technology for developing new sustainable battery materials. So this brings to the end of my talk, and I hope I can leave some time for questions. Let me repeat again the three messages I tried to emphasize in my talk here, with the hope that it is useful to you in thinking about how to strategize for the energy transition. Again, industry, startups, academia, national labs. These entities coming together is the key to Silicon Valley. This is very much our blood and DNA, and we have seen countless successes over the past 30 years across multiple fields, and the energy transition will be no different. We will see this diffuse interface as one of the primary enabling pillar. The second thing I highlighted today is systems level thinking. When we are approaching complicated problems, it's really important to exit your silo and think about how it is connected to other parts of the ecosystem, sometimes quite far away from your area of expertise. And we have learned sometime when you optimize the system, the outcome looks very different than when you just optimize one piece of the puzzle. And I think this is very much a necessary part to coordinate these multi-track R&D efforts. And then finally, as I just mentioned, the pace of R&D is incredibly important. We will not be able to achieve our goals unless the speed to new technology deployment increases substantially. So this concludes my talk. I hope that I have given you a sense of the learnings we have received here at Stanford over the past 20 years in thinking about how to deploy technologies for the energy transition. Now the transition is here. I hope these learnings will also inspire you to think about where the big opportunities might lie. Thank you.